DAAT and TAAT can score the same postings yet create completely different memory pressure. You'll compare DAAT and TAAT postings traversals and choose the lower latency strategy for this query. I'm Professor Pi, teaching search and IR with simple Python. A search engine has a simple job that gets difficult fast. A user types several terms, and the engine must find documents that match them, add their relevant scores, and return good results quickly. The challenge is not just scoring. It is deciding the order in which to walk through the matching documents. An inverted index stores a postings list for each term. Each list says which documents contain that term, often with a score already prepared by TF-IDF or BM25. For a multi-term query, we need to combine several sorted lists. Both approaches inspect the same underlying evidence. Their working memory and control flow are very different. We will build a small search example, run both traversal styles, and measure what each one keeps in memory. That makes the trade-off visible before you apply the idea to much larger indexes. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a shared set of postings, so both traversals solve exactly the same retrieval problem. This snippet builds one inverted index and selects the postings lists needed by a 3-term query. Each tuple contains a document identifier and a pre-computed term score, which could come from TFIDF or BM25. The query terms map to 3 sorted lists, while postings counts every score contribution each traversal must inspect. Keeping this input small makes overlapping documents and later score additions easy to trace. The output shows that the query spans 3 terms and 7 postings, establishing the shared workload for both algorithms. The sorting matters because DAAT will rely on document identifiers arriving in order, while TAAT can simply consume each list from start to finish. The first approach makes every term finish its work before the next term begins. This example implements term-at-a-time traversal by accumulating every posting into scores. TAAT finishes one term list before moving to the next, so default doct keeps a running value for every document encountered, anywhere in the query. Run TAAT also counts visits and returns stored, the number of live document accumulators. That state can become large for broad queries with many distinct matches. TAAT rank then sorts completed scores by descending value with document identifiers breaking ties. The output shows document 3 leading after 7 visits, while 4 document scores had to remain stored. This is direct and easy to implement, which makes TAAT useful when you need all final scores anyway. TAAT has the answer, but it has collected scores for every matching document before ranking anything. This code implements document-at-a-time traversal with a heap holding 1 cursor per postings list. Heap pop selects the smallest current document identifier. Contributions for that document are combined, and heap push advances only the list that supplied the posting. The heap frontier scales with the query term count, although out still materializes completed results for comparison in this teaching version. Same checks those results against the TAAT scores rather than assuming the loops are equivalent. The output confirms identical scores after 7 posting visits and exposes the 11 measured heap pushes and pops. DAAT sees one document's complete score before moving to the next document identifier. For more practical Python, data science, and search lessons, subscribe and keep building these ideas with me. Now that DAAT produces documents one at a time, we can avoid saving every completed score when only a few top results matter. This snippet converts the DAAT score stream into a bounded top TAA selection. Keeping every completed score can erase DAAT's memory advantage, so top stores only the 2 strongest candidates seen so far. The minimum item sits at top 0, letting heap replace discard the weakest candidate when a better document arrives. The negative document identifier preserves the earlier tie rule. Increasing k retains more possible results, but grows the candidate heap, while decreasing it saves memory and returns fewer documents. The output shows documents 3 and 1 surviving, with a peak candidate count of 2. This is the important DAAT payoff for ranked retrieval. Score a document, decide whether it belongs, then move on. A tiny example shows the mechanics, but the real choice becomes clearer when the postings lists grow wider. This example benchmarks both traversal functions on 3 wider postings lists. Repeat runs each function several times, and the minimum per query duration reduces some one-off timing noise without pretending to be a full production benchmark. This workload makes run TAAT maintain 6,000 accumulators, while run DAAT begins with a 3-entry frontier, but pays for repeated heap operations. Its returned outlist is still materialized. Increasing loops can stabilize the timing estimate, but makes the experiment run longer. The output identifies the locally faster traversal and places its latency beside the contrasting TAAT state and DAAT frontier sizes. That result is a local measurement, not a universal winner. When a search feature needs every matching document for later aggregation, TAAT can be the simpler choice. It naturally builds a complete document-to-score table. When a user only needs a small ranked page of results, DAAT with bounded top K selection usually has a stronger memory story. The heap work is not free, so measure it against your actual posting lengths, query sizes, and ranking needs. The key result is that both methods inspected 7 postings and produced the same scores. TAAT organized work around terms and stored every document it touched. DAAT organized work around documents and can release completed scores quickly when top K is integrated. Try changing K from 2 to a larger value and watch the candidate heap grow. Then, make the postings lists overlap less and compare how many document accumulators TAAT must keep versus the small DAAT frontier. What retrieval topic would you like to explore next, such as phrase queries, BM25 scoring, or query optimization? Subscribe for more clear, practical search and Python lessons.